Welcome to Sleepcast, probably the most boring podcast in the world. Sleepcast is created to help you relax, slow down, and gently drift off to sleep. There's nothing you need to remember and nowhere else you need to be. Simply get comfortable, close your eyes, and allow tonight's quiet story to carry you away. And now, we hand things over to our two hosts for today's episode. Rest well and enjoy.
Imagine standing out in a park on a perfectly sunny, cloudless summer day.
Right, just a beautiful, crystal clear sky overhead.
Exactly. The sky above you is this brilliant blue. You are miles and miles away from the nearest rainstorm.
You probably can't even see any dark clouds on the distant horizon.
Yeah, the sun is shining, birds are singing, and you just feel completely safe.
As you should, logically.
But in the next fraction of a second, a horizontal bolt of plasma could literally erupt from that distant storm, travel through the clear air, and strike the ground right next to you.
Which is just, it completely shatters our traditional understanding of weather.
It really does.
We are taught to treat the sky as this, passive ceiling, just an occasional inconvenience that might ruin a picnic.
Right, just bring an umbrella and you're fine.
Exactly.
Yeah.
But when you look at the raw thermodynamics and the sheer scale of the energy being released in our atmosphere, that passive ceiling idea just vanishes.
Today, we are taking a stack of incredible sources from the National Oceanic and Atmospheric Administration, the National Severe Storms Laboratory, the Met Office, and even the historical archives of the International Cloud Atlas.
It's a fantastic collection of material.
And the mission today is to completely transform how you, the learner, see the sky above you.
We're going to unpack the hidden architecture of clouds and the violent physics of thunderstorms.
And the electrifying history of how humans actually learn to classify and track lightning. So, okay, let's unpack this.
It's a lot to cover.
It is. But if you want to be the most well-informed person in the room during the next summer downpour, you really need to understand the factory that builds the storm.
Yeah, because before we can even get to the lightning, we have to talk about clouds.
Right. And the best place to start, according to the sources, is by dismantling a nearly universal misconception.
Oh, absolutely. If you ask anyone on the street what a cloud is made of, they will almost certainly tell you it's made of water vapor.
Which, that feels entirely logical, right?
It makes intuitive sense.
You boil a pot of water, you see steam rising from it, and it looks like a mini cloud. So you just assume the sky's doing the exact same thing.
Yeah, but that visual similarity is actually deceiving. Water vapor is a gas, and it is entirely invisible.
Wait, entirely invisible?
Completely. You are sitting in it right now.
Oh, weird.
When you step outside on a deeply muggy, humid day and the air just feels thick, that is water vapor. You cannot see it.
So if it's not vapor, what are we actually looking at when we see a cloud?
A cloud only physically manifests when a specific thermodynamic threshold is crossed. It happens when the air contains more water vapor than it can hold at its current temperature.
So the invisible gas is essentially forced to change its state.
Exactly. The mechanism is driven by temperature and altitude. As a parcel of air rises, the atmospheric pressure around it drops, which allows the air to expand.
And expanding air cools down.
Right. Cold air possesses less kinetic energy, meaning the water molecules are moving slower. Eventually, they slow down so much that they can no longer bounce off each other as a gas.
They lose their bounce.
Yeah, the intermolecular forces take over and they condense into a liquid.
But we aren't talking about giant raindrops just floating around up there.
No, these are microscopic. We are talking about droplets roughly 1/100th of a millimeter in diameter.
That is incredibly tiny.
They are so small that they can't even form on their own. They need a foundation to cling to.
Like what?
Dust, mostly.
Right.
These slowing water molecules grab onto microscopic bits of dust, pollen, or smoke that are just suspended in the atmosphere.
So that giant fluffy white mountain floating over your town is actually just a localized collection of billions upon billions of tiny liquid water droplets.
Yep, or ice crystals if the altitude is cold enough, just clinging to dirt and hanging in the air.
That's wild. But I want to focus on why that air is rising in the first place. Because it has to be pushed up to cool down.
It does.
I know the sun heating the ground is the classic trigger. Like the ground gets hot, it heats the air immediately above it, and that warm air rises to give us those puffy, cartoon-style cumulus clouds.
The classic summer day cloud, yeah.
But that can't be the only way, right? Or we'd only ever have one type of cloud.
You're right, topography plays a massive role, too. Consider a steady wind blowing across a flat plain that suddenly hits a mountain range.
It has nowhere to go but up.
Exactly. This forced descent is called orographic lift. It creates those massive, flat, layered stratus clouds that often drape over hillsides.
Oh, like when mountains look foggy.
Precisely. You also have weather fronts. Picture a massive, dense block of cold air moving across the landscape.
Like a cold front on the weather map.
Yeah, and when it collides with the lighter mass of warm air, the cold air acts like a wedge, literally forcing the warm air to slide up and over it.
Which generates what?
Vast gray sheets of nimbostratus clouds that can cover entire states.
Wait, let's connect the dots here. If the sun heating the ground just creates a nice puffy little cotton ball of a cumulus cloud, how do we cross the bridge from that to a towering, terrifying thunderstorm?
Well, the secret lies in the physics of the phase change we just discussed. When water vapor transitions from an invisible gas to a liquid droplet, it isn't a neutral event.
What do you mean?
The forming of those molecular bonds actually releases energy into the surrounding environment in the form of latent heat.
Hold on, I need to visualize this. The air had to cool down to force the water to condense, right?
Right.
But you're saying the actual act of condensing releases heat.
Think about the immense amount of energy the sun had to pump into a puddle of water to evaporate it in the first place.
Okay, a lot of solar energy.
That energy doesn't just disappear, it is stored in the water vapor molecules.
Ah, I see.
When those molecules finally cool, slow down, and snap back into a liquid state up in the cloud, all that stored solar energy is released backward into the surrounding air as heat.
That is just wild. It's kind of like a hot air balloon that somehow manufactures its own fuel and its own burner out of thin air as it flies.
That is a perfect analogy. The thunderstorm is the ultimate self-sustaining engine. It inhales warm, moist air from the ground.
And then what?
As that air rises and cools, the moisture condenses, releasing a massive burst of latent heat. This new heat warms the air inside the cloud, making it more buoyant than the clear air outside the cloud.
So it shoots up even faster.
Much faster. The updrafts inside a severe thunderstorm can reach speeds of 100 miles per hour.
100 miles an hour straight up.
Yes, carrying moisture higher and higher into the atmosphere, building the cloud into a towering giant.
But it can't just climb forever, right? It's going to hit a ceiling eventually.
It does. The vertical growth stops when it hits the tropopause, which is the boundary between the troposphere where all our weather happens and the stratosphere above it.
Let me test an analogy here. The tropopause isn't a physical roof like a concrete dome, right? It's a density barrier.
Exactly. It's a thermodynamic boundary.
So the storm is rising because it's warmer than everything around it, but the stratosphere is actually relatively warm because of the ozone layer absorbing UV rays.
Right. The temperature profile flips.
So the storm hits the tropopause and suddenly realizes, oh, I'm no longer the warmest thing in the room. It loses its buoyancy.
That's it. Exactly.
It's like a drop of oil rising through water and then hitting the surface.
Yeah.
You can't go into the air, so it just splatters outward.
The physics in that analogy hold up beautifully. That loss of relative buoyancy is exactly why the rising column of the thunderstorm flattens out against the tropopause.
Spreading horizontally.
Yes. Creating that terrifying, flat, anvil-shaped top we always associate with severe weather. The storm engine will keep churning violently as long as it has an intake of warm, moist air from the ground.
And here is the profound irony of the thunderstorm. The thing that ruins your weekend picnic, the cold rain, is actually the storm suffocating itself.
Yeah, the very product of the engine is its own undoing. As the storm matures, it produces massive amounts of rain and hail.
Which are heavy.
Very heavy. And these falling particles drag cold air down from the upper atmosphere with them, creating powerful downdrafts.
So it's basically pulling the stratosphere down.
Essentially, yes. When this avalanche of cold air hits the ground, it spreads out, creating a pool of heavy, cool air beneath the storm.
It's throwing a wet blanket over its own fuel source.
That's exactly what it's doing. The warm surface air is cut off. Without that inflow of moisture and heat, the updraft collapses.
The condensation stops.
And the massive atmospheric engine quietly starves to death, dissipating back into the sky.
We can track all of this today with radar, satellites, and supercomputers. But put yourself in the shoes of someone observing the sky 200 years ago.
It was a completely different world.
Imagine standing in a field in the early 1800s, looking up at this boiling, shape-shifting chaos. How do you even begin to organize it?
It was honestly one of the greatest taxonomic challenges in scientific history.
Because you can't just catch a cloud.
Right. Botany and zoology had physical specimens you could pin to a board or preserve in a jar. Clouds were ephemeral. They change every minute.
So how do we figure it out?
Well, the history of the International Cloud Atlas shows us that humanity first had to invent a specialized language just to agree on what we were looking at.
And the first guy to attempt this on a grand scale, Jean-Baptiste Lamarck, suffered a pretty legendary failure, didn't he?
He really did. Lamarck was a brilliant French naturalist. In 1802, he published a paper attempting to classify clouds into distinct forms.
And what was his theory?
He hypothesized that the shape of a cloud was a direct indicator of the atmospheric conditions that created it, which is true.
But nobody used his system. Our sources note that it completely flopped, largely because of a major branding error.
The branding was terrible. Lamarck chose to publish his groundbreaking meteorological taxonomy in the Annuaire Météorologique.
Which sounds fancy.
It sounds like a prestigious academic journal, sure, but it was actually a publication heavily padded with astrological forecasts and weather prognostications based on moon phases.
He put a genuine scientific breakthrough next to a horoscope.
Exactly. In the early 19th century, the hard sciences were fighting a desperate battle to distance themselves from mysticism, alchemy, and astrology.
So he just torpedoed his own reputation.
By associating his work with the occult, Lamarck destroyed his own credibility. Furthermore, he used French terminology.
Why was that a problem?
Well, science was striving for international collaboration, and localizing the language created an immediate barrier for German or English scientists.
Which sets the stage perfectly for Luke Howard just 1 year later, in 1803.
Ah, Luke Howard.
Howard was an English pharmacist and an amateur meteorologist, and he completely solved Lamarck's branding problem.
He really did. Howard recognized the power of the Linnaean system. That's the biological taxonomy that gave us Homo sapiens.
Oh, he used Latin.
Yes. Linnaeus used Latin, the universal language of scholars. Latin felt permanent, objective, and stripped of local cultural baggage.
It sounds more scientific.
By assigning Latin names to the clouds, Howard wasn't just describing them, he was elevating them to the status of recognized scientific entities.
And he kept it beautifully simple. He proposed 3 fundamental building blocks for all clouds. I'm going to look closely at these because we still use them every single day. First, cirrus.
Cirrus translates from Latin as a curl or a lock of hair.
Like those wispy ones.
Exactly. Howard used this to describe the high, wispy, feather-like clouds. He correctly deduced that these forms represented a unique atmospheric state.
Which we now know is due to ice.
Right. They are composed entirely of ice crystals high in the troposphere.
Second, cumulus.
Meaning a heap or a pile. This perfectly describes the towering, cauliflower-shaped clouds driven by the thermal updrafts we discussed earlier.
The hot air balloons. And finally, stratus.
Meaning a layer or a sheet. The broad, featureless blankets of gray that cover the sky during forced orographic lift or frontal collisions.
And Howard's true genius wasn't just picking 3 neat words, was it?
No, it was the realization that the atmosphere is fluid and clouds transition. He designed a modular system where these 3 names could be combined to describe intermediate states.
So if you see a cloud that is both a sheet and a heap, you call it stratocumulus.
Exactly, you just combine the terms.
Over the next century, the global scientific community realized they had a working operating system, and they started writing new code for it.
They did. In 1840, the German meteorologist Kainz officially adds that stratocumulus classification.
And then in 1855, a French observatory director named Renou introduces the prefix alto.
Alto indicates a middle-tier altitude. This allowed meteorologists to differentiate between a high, icy cirrocumulus, a low, watery stratocumulus, and the mid-level altocumulus.
Why did the height matter so much?
The height of the cloud was a massive clue to the atmospheric pressure and temperature profile above the observer.
I love the story of Poe in 1863 observing the sky from Havana, Cuba.
He's a fascinating figure.
He wanted to add fracto for clouds that look torn or broken by the wind, and globo for those eerie, pouch-like mammatus clouds that hang down like udders.
Those are terrifying to look at, by the way.
Yeah, they are. But our sources point out he didn't get the credit he deserved because he got arrogant.
He overplayed his hand.
He tried to tear down Howard's entire Latin system and replace it with his own overly complex invention.
It is a classic scientific cautionary tale. The community will accept incremental additions to a robust system, but they will violently reject a complete overhaul if the current system is already functional.
But they just ignored him.
Pretty much. Poe's specific observations were brilliant, but his political approach to taxonomy failed. Instead, the community embraced additions from people like Weilbach.
And Weilbach gave us the big one, the cumulonimbus.
Combining the heap, cumulo, with the Latin word for a rainstorm, nimbus, the towering rainmaker.
But formalizing this entire cloud atlas required immense physical labor to verify, right? In 1887, Hildebrandsson and Abercrombie took all these disparate Latin names and rigorously mapped them to 4 specific altitude levels.
The physical dedication of these early scientists is staggering.
The physical labor part is what gets me. The sources talk about Ralph Abercrombie's dedication. To prove that a cumulus cloud in England was physically identical to a cumulus cloud in the tropics, this man booked passage on ships and sailed around the world twice.
Twice. Just looking at clouds.
Picture a Victorian gentleman in the 1880s standing on a pitching deck amidst salt spray in the Pacific Ocean, meticulously sketching cloud formations just to verify that the thermodynamics of the atmosphere are mathematically consistent across the entire planet.
It's incredible. And his voyages prove that Luke Howard's system wasn't just a convenient European naming convention, it was a universal physical truth of the Earth's atmosphere.
And this all culminated in a big conference, right?
Yes. The 1891 Munich Conference, which led to the publication of the first International Cloud Atlas in 1896. It featured 28 color plates in 3 languages.
But then the perspective completely shatters in the 1920s and 30s.
Aviation changed everything.
Right. For 100 years, scientists were stuck on the ground looking up at the belly of the clouds. And then human beings learned to fly.
Aviation forced meteorology to evolve from a 2D observational science to a 3D thermodynamic science. Pilots were no longer just looking at the flat bottoms of clouds.
They're up in them.
They were flying alongside them, diving through them, and looking down on them from above.
They realized that these weren't just paintings on a ceiling. A cumulonimbus isn't just a dark shape. It is a violent 3-dimensional room full of turbulence and ice.
The International Cloud Atlas had to be completely overhauled to incorporate this new spatial data. Meteorologists began to map the internal structures, realizing that clouds were active participants in global heat transfer.
But flying through these structures also brought pilots face-to-face with the most dangerous weapon the cumulonimbus possesses.
Which brings us into the belly of the beast. We need to talk about lightning.
Yes. We established that the storm is a giant thermodynamic engine, pulling in warm air and spewing out rain. But how on earth does water and ice generate an electrical voltage powerful enough to rip a hole in the atmosphere?
To understand the electrical generation, we have to look past the macro scale of the updraft and focus on the microscopic violence happening inside the cloud.
Microscopic violence, I like that.
The primary agent of charge separation in a thunderstorm is a type of precipitation called graupel.
Graupel. G-R-A-U-P-E-L. What exactly is it?
Think of it as soft hail. It forms when supercooled water droplets freeze onto a falling snowflake.
So they're like tiny snowballs.
Basically, these are dense, icy particles ranging from 1/4 millimeter to a few millimeters in diameter.
Okay, so we have these tiny snow pellets. Now put them inside the chaotic updraft we built in Section 1.
That updraft is pushing millions of tiny, supercooled liquid water droplets and microscopic ice crystals upward at incredible velocities.
While the graupel is falling.
Exactly. The heavier, denser graupel is falling downward through that exact same column of air.
It's a microscopic highway with traffic moving in opposite directions at high speed.
Millions of collisions occur every single second. And laboratory studies on cloud physics reveal something fascinating about these impacts: the triboelectric effect.
Triboelectric. What happens during the collision?
When the falling graupel clashes into a rising ice crystal, a physical transfer of electrons takes place.
This is where I go back to the classic analogy of walking across a carpet in fuzzy socks.
It's the perfect way to understand it.
Your socks physically rub against the carpet fibers, stripping electrons and building up a negative static charge on your body until you touch a doorknob and get zapped.
The mechanism in the cloud is nearly identical, just scaled up to catastrophic proportions.
Yeah.
During the collision, the graupel strips electrons from the lighter ice crystals.
So the graupel steals the negative charge.
Yes. The graupel becomes negatively charged, And because it is heavy, it continues to fall, pooling in the middle and lower layers of the thunderhead.
And the ice crystals.
The smaller ice crystals, now stripped of electrons and carrying a positive charge, are swept by the updraft to the very top of the anvil.
So the thermodynamic engine has just built a macroscopic battery.
A very, very big battery.
The top of the cloud is positively charged, and the vast, dark underbelly of the cloud is intensely negative. But the ground beneath the storm isn't just a neutral bystander, is it?
Not at all. The intense negative charge pooling at the bottom of the cloud exerts a powerful electromagnetic force on the Earth below it.
It pushes back.
It literally repels the negatively charged electrons in the ground, pushing them deep into the soil. This leaves the surface of the Earth and everything on it, including trees, buildings, and people, with a strong, localized positive charge.
Nature despises an imbalance. It wants to neutralize those two poles.
The atmosphere acts as a massive insulator, a dielectric layer trying to keep the positive and negative charges apart. But as the storm churns and the grapple keeps colliding, the electrical potential grows exponentially.
Until it snaps.
Eventually, the voltage becomes so extreme that the insulating capacity of the air is overwhelmed. The air experiences dielectric breakdown, rapidly converting from an insulator into a conductor.
And the resulting discharge is just terrifying when you look at the raw numbers. The sources note that a lightning channel heats the air around it to 50,000 degrees Fahrenheit.
That heat is almost incomprehensible. To put that in perspective, the surface of our sun is roughly 10,000 degrees Fahrenheit.
So it's 5 times hotter than the sun.
A lightning bolt is 5 times hotter than the surface of a star, generating that heat in a fraction of a millisecond.
And that flash heating is the sole cause of thunder.
Yes. Thunder has nothing to do with clouds physically colliding. When the lightning channel superheats the air to 50,000 degrees, the gases in the air expand explosively.
Like a bomb going off.
Exactly. This rapid, violent expansion creates a supersonic shock wave that ripples outward in all directions.
You've probably stood on your porch during a storm, counting the seconds after a flash to see how far away the lightning is.
The classic trick.
What you're actually doing in that moment is calculating the propagation of a shock wave through a fluid. Light travels at 186,000 miles per second, so the visual flash hits your eyes instantly. But sound is sluggish.
Very sluggish in comparison.
It only moves through the air at about 1/5 of a mile per second.
Which gives us the remarkably simple and accurate 5-second rule. When you see the flash, you start counting. For every 5 seconds that pass before you hear the thunder, the lightning strike was 1 mile away.
10 seconds means it is 2 miles away.
And the tone of the thunder also gives you clues about distance.
Because a close strike sounds like a terrifying tearing crack, but a distant one is just a low rumble. Why is that?
Well, the initial explosion contains a wide spectrum of sound frequencies. If you are close, you hear the high-frequency tearing sound.
The crack.
Right. But as the acoustic wave travels through miles of atmosphere, the air acts as a natural filter, absorbing the high frequencies and leaving only the deep, low-frequency rumbles to reach your ears.
That makes perfect sense. But I want to zoom in on the anatomy of the strike itself, because when that voltage finally overcomes the air's insulation, it doesn't just shoot a straight laser beam down to the ground.
No, the mechanics of the spark are incredibly complex. What the human eye perceives as a single instantaneous flash is actually a complex multi-step sequence. It begins with the stepped leader.
Which is completely invisible to us.
A stepped leader is a channel of negative charge that begins zigzagging downward from the cloud base. It moves in distinct steps of about 50 yards at a time.
50 yards, then it stalks.
It pauses for a fraction of a millisecond and then branches out to find the path of least resistance through the air's density and humidity. It is literally carving a conductive wire out of thin air.
And while this invisible root system of negative charge is probing downward, the positive charge on the ground is reacting.
Strongly. As the stepped leader gets within a few hundred yards of the surface, the electrical field at the ground becomes intense. Tall, conductive objects like radio towers, oak trees, or a person standing in a field
will suddenly launch channels of positive charge upward into the air.
Exactly. These are called streamers.
So the ground is actively reaching up, trying to grab the lightning.
And the moment one of those upward streamers connects with a branch of the downward stepped leader, the circuit is closed. A conductive channel now exists between the cloud and the ground.
And that triggers the main event.
This triggers the return stroke.
This is the part that blows my mind. The brightest part of the flash, the massive surge of energy that we actually see, is not traveling down from the cloud, it is traveling up from the ground.
It is entirely counterintuitive. The massive pool of positive charge on the ground rushes upward through that newly created channel into the cloud at a third of the speed of light.
That's roughly 60,000 miles per second.
The visual brightness moves upward, even though electrons are technically flowing downward. And remarkably, the core of that plasma channel is only 1 to 2 inches in diameter.
A 2-inch pipe of star-hot plasma. Now, what we just described is the most common type of strike, negative cloud-to-ground flash or negative CG.
Right, the standard bolt.
But the sources highlight a much rarer, much more destructive variant, the positive CG.
Recall that the top of the thunderstorm anvil holds the massive pool of positive charge. Occasionally, a step leader will originate from that high altitude and attempt to strike the ground.
Which is way further away.
Because it is starting from much higher up, it has to travel through a significantly thicker layer of insulating air to reach the Earth.
So it needs a massively higher voltage just to punch through.
Precisely. It requires an enormous electrical potential. When a positive CG finally connects, it delivers a staggering amount of current. Furthermore, positive strikes often have a continuing current.
What does that mean for this stuff on the ground?
It means the electrical flow is sustained for a fraction of a second longer than a negative strike. This prolonged thermal exposure is what ignites forest fires and explodes transformers.
But even a positive CG doesn't terrify me as much as the scenario we opened the show with. The bolt from the blue. This fundamentally alters the safety calculus of being outdoors.
It really does. A bolt from the blue is a specific type of positive cloud-to-ground lightning. Instead of striking straight down beneath the cloud base, the leader exits the side of the thunderhead and propagates horizontally through clear, cloudless air.
Just shooting out sideways.
It can travel 5, 10, even 15 miles away from the parent storm before angling downward and striking the ground.
That means you could be sitting at a baseball game, bathed in sunlight, looking at a blue sky overhead, and you can still be struck by a fatal bolt of lightning from a storm you can barely see on the horizon.
It happens.
The standard advice of, if you can hear thunder, you're close enough to be struck, isn't just an abundance of caution, is it? It is a mathematical reality of horizontal lightning channels.
It is the ultimate testament to the unpredictable reach of the storm's electrical field. And the sky holds even stranger phenomena. The vast majority of lightning never actually touches the ground at all.
Right, we have intracloud lightning,
which arcs between the positive and negative regions inside the same cloud, illuminating the entire structure from within like a glowing lantern.
People often call that heat lightning on summer nights, thinking it's some special kind of weather that doesn't produce rain or thunder.
Heat lightning is a persistent myth. It is just a standard thunderstorm that happens to be very far away.
So why don't we hear it?
The curvature of the Earth and the distance prevent you from hearing the thunder. The light from the intra-cloud flashes has to travel through miles of hazy summer atmosphere to reach your eyes.
And the air acts like a filter again.
Exactly. The air scatters the shorter blue wavelengths of light, leaving only the reds and oranges, which makes the flashes look like a silent, eerie sunset. But someone standing under that storm is experiencing a very real, very loud downpour.
The sources also detail something called spider lightning, which looks exactly how it sounds. Long, sprawling, horizontal branches of electricity that crawl across the underside of stratiform clouds at the back of a storm system.
It's beautiful, but eerie.
But if we want to talk about truly alien electrical phenomena, we have to look above the storm. We have to talk about TLEs.
Transient luminous events. These occur in the upper atmosphere, in the mesosphere, and the ionosphere, far above the weather we experience on the ground.
And they were basically a rumor for decades, right?
For much of the 20th century, commercial airline pilots flying at high altitudes would nervously report seeing massive, glowing, colorful shapes shooting upward into space above large thunderstorms.
And the scientific establishment essentially gaslit them for decades.
They did. The reports sounded too much like science fiction. Pilots described glowing red jellyfish and towering blue cones.
This sounds completely made up.
Because these events lasted for mere milliseconds and left no physical trace, meteorologists largely dismissed them as reflections on the cockpit glass or simple optical illusions.
So when did we actually believe them?
It wasn't until the late 1980s and early 1990s when researchers operating low-light video cameras on the space shuttle and in high-altitude aircraft managed to capture them on film that the scientific community realized the pilots were telling the truth.
So we have an entire zoo of upper atmospheric electricity. Let's start with the most famous, Red sprites.
Red sprites are intimately connected to the powerful positive cloud-to-ground strikes we just discussed.
How so?
When a massive positive CG dumps an enormous amount of charge into the ground, it leaves a sudden, intense electrical imbalance in the atmosphere above the cloud. This imbalance triggers a massive, weak electrical discharge in the mesosphere, some 30 to 50 miles above the ground.
But why are they red? And why do they look like giant glowing jellyfish?
The color is a product of atmospheric chemistry. At that extreme altitude, the atmosphere is thin, and the discharge excites the nitrogen molecules in the air.
And nitrogen glows red.
When those nitrogen electrons drop back down to their base energy state, they emit photons in the red spectrum. They form complex branching structures that can be 30 miles wide, dangling tendrils downward toward the cloud top.
Then we have blue jets.
Blue jets are different. Rather than being triggered by a strike to the ground, they erupt directly out of the electrically charged tops of the thunderheads.
Shooting straight up.
They shoot upward in a narrow cone at hundreds of thousands of miles per hour, reaching altitudes of 25 to 30 miles before dissipating.
Also nitrogen.
The deep blue color is also caused by nitrogen excitation, but at a lower altitude where the atmospheric density is different, altering the emission spectrum.
And finally, the elves. They sound small, but they're the biggest of them all.
The acronym stands for emission of light and very low-frequency perturbations due to electromagnetic pulse sources.
Say that 5 times fast.
Right. An ELVE is an unimaginably massive, rapidly expanding disk of glowing red light that can span 300 miles across the sky.
How does a storm create a 300-mile-wide glowing halo in space?
When an incredibly powerful lightning strike occurs, it doesn't just release light and heat. It emits a massive electromagnetic pulse, an EMP.
Like a nuclear bomb.
Similar concept. This invisible shock wave of radio frequency energy radiates upward at the speed of light. When that spherical wave crashes into the ionosphere, which is a layer of the atmosphere rich in charged particles about 60 miles up, the energy excites the gases in a massive expanding ring.
And how long does it last?
It lasts for less than 1,000th of a second.
It is stunning to realize that every time a severe storm rolls over your house, there is a silent, invisible light show of red jellyfish, blue cones, and 300-mile-wide glowing halos happening at the very edge of space, and we are completely blind to it.
The complexity of these phenomena, from the invisible stepped leaders creeping through the air to the electromagnetic pulses ringing the ionosphere, demonstrates why humanity couldn't just passively observe lightning.
We had to do something about it.
We had to find a way to track it, map it, and survive it.
Which brings us into the fascinating history of catching the spark. And we have to start with the founding father of electricity, Benjamin Franklin. In the mid-1700s, lightning was the leading cause of catastrophic fires in wooden cities and on sailing ships.
Franklin hypothesized that lightning was a massive discharge of static electricity, identical to the sparks he was generating in his laboratory, just on an atmospheric scale.
And he figured out how it burned things down.
He realized that the danger wasn't just the strike itself, but the resistance of the materials it traveled through. When millions of volts pass through a wooden roof, the electrical resistance generates massive heat, causing the wood to explode and ignite.
So his solution, the lightning rod, was beautifully pragmatic. He wasn't trying to build a force field to repel the lightning.
Not at all. He built a conductive highway. A lightning rod is a pointed metal spire placed at the highest point of a structure, connected to a thick copper or aluminum cable that runs down the side of the building and is buried deep in the moist earth.
The path of least resistance.
Exactly. When the downward stepped leader approaches, the lightning rod provides a concentrated point for the upward positive streamer to launch from. It invites the strike.
He wants to be it.
Once the connection is made, the massive current of the return stroke bypasses the resistive wooden house entirely, flowing harmlessly down the highly conductive metal cable and dissipating into the ground.
It's an incredible piece of mechanical engineering that saved countless lives. But dealing with a strike as it happens is one thing. Detecting a storm before it arrives is another challenge entirely. And our sources point to 1895 and a Russian physicist named Alexander Popov as the pioneer of remote detection.
Popov was fascinated by the electromagnetic properties of lightning. He understood that a massive electrical discharge didn't just produce visible light, it emitted invisible waves of electromagnetic energy.
What we now call radio waves.
Yes. He wanted to build an instrument that could detect these invisible waves to warn observatories of approaching severe weather.
The mechanism he used is just brilliant. He built a device around a component called a coherer. Let's break down the physics of how a coherer actually works, because it's vital to understanding what happened next.
A coherer is remarkably simple. It consists of a glass tube filled with loose metal filings, usually iron. This tube is placed in an electrical circuit.
Okay, so a tube of iron dust.
Under normal conditions, the loose iron filings rest haphazardly against each other. The electrical resistance between all those loose pieces of metal is very high, so no current flows through the circuit.
It's like a broken wire.
Exactly. But when a strong electromagnetic wave, like the pulse generated by a distant lightning strike, washes over the glass tube, the radio frequency energy induces a microscopic voltage in the filings.
Which does what to them?
This causes them to instantly align and stick together, or cohere.
They fuse into a solid conductive bridge.
The resistance drops to near zero, the circuit closes, and the current flows, which Popov used to ring a bell. A mechanical tapper would then immediately strike the glass tube to shake the filings loose again, resetting the device for the next lightning strike.
Lightning flashes 10 miles away, sends out an invisible radio wave, the iron filings align, the circuit closes, the bell rings. You just built a weather radar. But here's where it gets really interesting. The poetic irony of this invention is what truly changed the world.
Popov quickly realized the broader implications of his weather instrument. If this glass tube of iron filings could detect natural radio waves generated by lightning, it could logically detect artificial radio waves generated by humans.
Oh, wow.
He adapted his lightning detector to transmit and receive controlled electrical pulses in Morse code.
A device built to warn us about lightning, a natural force that notoriously destroys electronics and disrupts communications, was the exact technological mechanism that gave birth to wireless radio communication.
It is a stunning pivot in human history. The background noise of the universe taught us how to talk to each other across vast distances.
So Popov gives us the radio, which is amazing. But a single coherer bell ringing just tells you that lightning exists somewhere within a 50-mile radius. It doesn't tell you if the storm is to the north, south, moving toward you, or moving away. How did the scientific community move from detecting a general pulse to actually plotting strikes on a map?
In the mid-20th century, following World War II, meteorologists adapted a navigation technique used for ships called time of arrival, or TOA, geolocation.
Like triangulation.
Essentially, yes. Imagine setting up 3 or 4 highly sensitive lightning detection antennas spread across hundreds of miles of terrain. When a lightning bolt strikes, it emits an electromagnetic pulse that travels outward at the speed of light.
Right.
However, because the receiving stations are at different distances from the strike, that pulse will arrive at each station at a fractionally different microsecond.
So if Station A hears it a millisecond before Station B, you know the strike was closer to Station A.
By feeding those microscopic time differentials into a central computer, you can calculate intercepting hyperbolas and pinpoint the exact geographic coordinates of the lightning strike with incredible precision. This allowed meteorologists to plot real-time maps of lightning activity across entire continents.
And computing power only accelerated this. The sources mention lightning mapping arrays, or LMAs. We went from dropping pins on a 2D map to building 3D models of the lightning channel.
LMAs use dense networks of antennas and extremely precise GPS timing to track the radio frequency radiation emitted by the stepped leaders themselves. They don't just record where the bolt hit the ground.
They track the whole path.
They track the propagation of the electrical channel as it branches and zigzags through the interior of the cloud in 3 dimensions.
But even with a sprawling network of ground antennas, we were still fundamentally looking up at the sky. We were missing strikes over the open oceans, and we couldn't see the global picture. To truly tame the sky, we had to go above it.
The space age completely revolutionized lightning detection. In the late 1990s, NASA launched the Tropical Rainfall Measuring Mission, which carried an instrument called the Lightning Imaging Sensor.
Detecting a flash of light from space sounds easy, but doing it during the daytime, when the sun is reflecting off the blinding white tops of the clouds, has to be an engineering nightmare.
It required specialized optics. The sensor was designed to look for very specific, narrow wavelengths of light emitted by the oxygen and nitrogen plasma in a lightning channel, filtering out the broad-spectrum glare of sunlight.
And what did that show us?
This allowed us to map global lightning distribution, revealing that 90% of all lightning occurs over land masses rather than oceans, due to stronger thermal updrafts over land.
And today, we rely on the Geostar series satellites, operated by NOAA.
These satellites carry the Geostationary Lightning Mapper, or GLM. Unlike earlier sensors that orbited close to the Earth and only saw a specific area for a few minutes at a time, the GLM sits in geostationary orbit, 22,000 miles above the equator.
So it just stares at us all day.
It continuously stares down at the entire Western Hemisphere, tracking every single optical flash over the Americas and the surrounding oceans, 24 hours a day.
And having a permanent eye in the sky has allowed us to document phenomena that ground networks simply couldn't capture. The sources highlight a specific record that was shattered on April 29, 2020.
The World Meteorological Organization certified the longest lightning flash ever recorded. It occurred over the southern United States and stretched an incomprehensible 477 miles.
One single continuous electrical discharge connecting storm systems from Texas to Mississippi. A mega flash nearly 500 miles long.
And we are no longer just mapping it as it happens, we are predicting it before the first spark is even generated.
Which feels like magic, considering how chaotic the electric field is. You can't predict the exact moment a stepped leader will form.
You cannot predict the specific strike, but you can predict the thermodynamic engine. Modern artificial intelligence models, like NOAA's Prob-Severe Lightning Cast, continuously ingest the visual and infrared data from those geostationary satellites.
What is the AI actually looking for?
The AI looks at the cooling rate of the cloud tops, the expansion of the anvil, and the specific texture of the cloud surface to calculate the probability that a developing cumulus cloud will begin producing lightning within the next 60 minutes. We can watch the engine rev up and warn people before the dielectric breakdown even begins.
We have taken an immense journey today. We started with microscopic water vapor molecules losing kinetic energy and clinging to specks of dust.
A lot of tiny specks of dust.
We watched those droplets release latent heat, building towering thermodynamic engines that smash against the density barrier of the tropopause. We watched Victorian meteorologists sail the globe to prove the universality of Latin cloud names.
We unpacked the violent triboelectric collisions of graupel and ice, building massive atmospheric batteries that rip 50,000-degree plasma channels through the air.
You discovered growing red jellyfish touching the edge of space, and we traced the technological leap from Benjamin Franklin's simple metal rod to geostationary satellites mapping 500-mile megaflashes from orbit.
We have thoroughly dissected the architecture and the energy of the sky.
Hopefully, the next time you, the learner, look up at a darkening summer sky, you aren't just thinking about running to your car before the rain starts. You are looking at a massive, churning thermodynamic machine, steeped in centuries of human discovery, observation, and awe. So what does this all mean? Where does this leave us?
Well, it leaves us looking even further outward, beyond the boundaries of our own planet. There is a profound detail hidden in our sources that connects our local weather to the deep universe.
I love this part.
When we discussed ELVs and those upper atmospheric electrical phenomena, the research notes they are often associated with terrestrial gamma ray flashes, or TGFs.
So, gamma rays, the storms are producing radiation.
Powerful bursts of gamma radiation, and the leading theory for how these are generated involves cosmic rays.
Particles traveling from deep space.
Highly energetic subatomic particles, often the remnants of distant exploding supernovae, constantly bombard the Earth's atmosphere from deep space. When these cosmic rays strike the intense electrical fields above a developing thunderstorm, they can act as a trigger.
Triggering what exactly?
Violently accelerating electrons to near the speed of light, effectively turning the storm into a natural particle accelerator.
I want to make sure I'm fully grasping the scale of this. If cosmic rays from deep space are required to seed these gamma ray flashes and trigger these upper atmospheric cascades, does that mean the localized thunderstorm I watch from my window might be actively interacting with the energy of a dying star millions of light years away?
It suggests that the lightning in our atmosphere is not an isolated earthly phenomenon. The electrical discharge in your backyard may very well be influenced by the violent deaths of stars across the universe, connecting the rain on your roof to the deepest reaches of the cosmos.
Let that mind-bending reality mull over in your thoughts the next time you sit on your porch and listen to the thunder roll.
And that brings another quiet episode of Sleepcast to an end. Thank you for spending this time with us. We hope our two hosts helped you relax, slow your thoughts, and perhaps drift gently off to sleep. New episodes of Sleepcast are released every day, 7 days a week, all year round. Follow Sleepcast on the podcast app you are using now, so new episodes are added automatically, and you can be notified whenever another wonderfully boring story is released. Until next time, sleep peacefully and good night. Sleepcast, probably the most boring podcast in the world.